today we are going to have a review session where we will essentially try to revise certain concepts on entropy by asking some short questions. So, I have projected the questions on the screen, but I will read these questions out and we will discuss these questions one by one. So, these questions are relating to state whether the following statements are true or false. So, certain statements are given, you have to say whether these are true or false, and in case you are able to give the correct answer, you also have to justify it. Okay. So, the first question is all isothermal processes must be reversible. This is the first statement. So, true or false? So, let us try to analyze this. Let us say there is a piston cylinder arrangement and there is a heat transfer from a thermal reservoir. Let us say the temperature within the system is T1, which is less than T reservoir, so that there is a heat transfer. So, if this temperature T1 of the system remains the same, then it is an isothermal process for the system, and if it is isothermal, it is supposed to be a very slow process, so that it is a reversible isothermal process. However, the reversible isothermal process, by reversible we mean internally reversible, but if you look at this temperature difference between the thermal reservoir and the system boundary, there may be a finite temperature difference. So, isothermal may assure internal reversibility, but it will never assure total reversibility. It will be totally a reversible process if this T reservoir minus T1 is some delta T, very small, tending to 0, then it is reversible, externally reversible. Otherwise, it is not externally reversible, and we can say that it is just an internally reversible process. So, all isothermal processes must be reversible, this statement is not correct. Let us consider the second statement. Cyclic integral of del Q may tend to 0 for irreversible heat engines. So, cyclic integral of del Q. So, let us say that there is a heat engine which takes heat QH, rejects heat QL and does some work W in a cyclic process. So, cyclic integral of del Q is QH minus QL. Can it tend to 0 for an irreversible heat engine? Surely, because the difference of this is work done, and if the engine is highly reversible, the work done will be less and less, and therefore, in the limiting condition for a highly reversible situation, this may tend to 0. The third question is a process with no net change in the system entropy must necessarily be reversible and adiabatic. So, a process with no net change in entropy must necessarily be reversible and adiabatic. See, let us write the expression for change in entropy of the system. S2 minus S1 is equal to Q12 by T plus S gen. So, what is saying is that this is 0. How can this be 0? There are some possibilities. One is it is a reversible adiabatic process. If it is reversible, entropy generation is 0, if it is adiabatic, Q12 is 0. However, there could be some other case also when this is 0. When this is 0, for example, this is some minus positive number A. When this is negative, when heat is transferred from the system to the surroundings, and let us say this is plus A. So, then the total is 0, but it is not a reversible and adiabatic process. So, net change in entropy is 0 does not mean it is an isentropic process. Isentropic means the entropy remains same throughout the process, not just the final entropy minus initial entropy is 0. So, this is a case when the change in entropy at the end of the process is 0, but it is not reversible and adiabatic. So, a process with no net change in system entropy need not necessarily be reversible and adiabatic. Let us consider the fourth question. All slow processes must necessarily be reversible. So, this is also not true, because all slow processes must necessarily be internally reversible, but they may be externally reversible. So, if they are externally reversible, that means the net process becomes irreversible. The next question is, throttling of an ideal gas is approximately an isothermal process. So, throttling, the process of throttling is something like this. So, you have a throttle valve and across the valve the fluid is flowing in such a way that there is no scope of any heat transfer or work done, and if you neglect changes in kinetic energy and potential energy, the first law for a steady flow process will tell that HI equal to HE. Remember that this does not mean that it is an isenthalpic process. The enthalpy does not remain same, it is just the enthalpy before, immediately before throttling is same as enthalpy immediately after throttling, but we are talking about an ideal gas. So, now this means that dH, so HI minus HE equal to 0. So, if it is a constant specific heat, even if it is a constant specific heat, it means Cp into Ti minus Te equal to 0, not for all ideal gas, only for ideal gas with constant specific heat. But even then you cannot say that it is an isothermal process. Why? Because it is for an ideal gas with constant CpCv, this means that the temperature before throttling is same as temperature after throttling, but this does not mean that temperature remains same throughout the process. So, it is not an isothermal process. Next question, area under the closed loop representing a thermodynamic cycle in a TS diagram signifies the net work done in a cyclic process. So, if you have a TS diagram and you have an area enclosed in the TS diagram, so the area enclosed in the TS diagram in a cyclic process, so that is integral of TdS, that will be del q provided it is a reversible process. So, if it is a reversible process, then of course this area also represents the work done, because cyclic integral of heat is equal to cyclic integral of work from the first law of thermodynamics. But if the process is such that it is not a totally reversible process, then you cannot write del q equal to TdS, and then this equivalence will not be there. Next question, a process with 0 net change in entropy must necessarily be isentropic. So, this is the same question that we had here. 0 net change in entropy means S2 minus S1 is equal to 0. So, S2 minus S1 is equal to 0 does not mean it is an isentropic process, because it just indicates that the final entropy is same as initial entropy, but it does not assure that entropy remains constant throughout the process. Next question, a piston cylinder arrangement contains water at 40 degrees centigrade. Heat is transferred into the cylinder from a heat source at 100 degrees centigrade and water expands in a quasi equilibrium process. The process is reversible. Clearly the cylinder, the water expands in a quasi equilibrium process, that means it is internally reversible. However, there is a temperature difference between the system and the heat source. Heat source is 100 degree centigrade and system boundary is at 40 degree centigrade. So, because of this finite temperature difference across which heat transfer is taking place, it is an externally irreversible process. Therefore, the process is not reversible, it is only internally reversible but not externally reversible. Next question, a system undergoes change in state from state 1 to state 2 by a reversible and irreversible process. The change in entropy of the system is greater in the irreversible process. This is not true, because when the system goes from state 1 to state 2, the change in entropy S2 minus S1 does not depend on the path, it depends only on the end states 1 and 2, because it is a point function, the entropy is a point function. The next question, the entropy of a fixed mass of ideal gas decreases in every isothermal compression. So, entropy of a fixed mass of an ideal gas decreases in every isothermal compression. So, let us try to address this question. So, let us try to use this TdS relationship, TdS is equal to dH minus VdP. For an ideal gas, dH is Cp dt, isothermal means dt is 0. So, ds is minus VdP by T, compression means pressure increases, right. So, dP is positive, specific volume is positive and this is absolute temperature, it is always positive. So, ds is negative, that means entropy of a fixed mass of an ideal gas decreases in every isothermal compression. Next question, the specific internal energy, enthalpy and entropy of an ideal gas are each functions of temperature alone. So, internal energy and enthalpy of an ideal gas are functions of temperature alone, but entropy is not, right. Recall the formula for change in entropy of an ideal gas with constant Cp/Cv. So, S2 minus S1 is Cp ln T2 by T1 minus R ln P2 by P1. So, you can see that entropy of an ideal gas will depend on temperature. So, entropy of an ideal gas is not is a function of temperature as well as pressure, whereas internal energy and enthalpy are functions of temperature only, but entropy is a function of temperature and pressure or temperature and specific volume, right. So, this statement is not correct. Again I am repeating, the specific internal energy and enthalpy are functions of temperature only for an ideal gas, but entropy is a function of the temperature as well as pressure. Next question, a process that violates second law violates the first law too. This is not correct, because second law talks about the directionality of a viable process. So, according to first law, if energy balance is satisfied, you can still have heat transfer from a lower temperature body to a higher temperature body without any work input. However, according to second law, such a process will not be feasible until and unless you give a work input. So, even though you satisfy energy balance, which is the essence of first law, the second law may not be satisfied. So, a process that violates second law violates the first law too is is not correct, in a sense that a process that violates second law may not violate first law. Energy balance is satisfied, but second law is not satisfied. Next question, one corollary of the second law states that the change in entropy of a closed system must be greater than or equal to 0. So, the change in entropy of a closed system, if you see, this is the change in entropy of a closed system. Can we guarantee whether this is positive, negative or 0? We do not give a guarantee. See, very many times we loosely say that entropy always increases, but we do not mention that it is the entropy of the universe, system plus surrounding together, that increases. Entropy of a system or surrounding separately, those might either increase or decrease or remain the same. Sum total of entropy of the system and surrounding, if you consider, that will always increase. So, for example, entropy of a system can decrease. How it can decrease? Like if you have heat rejection, then this is negative for heat rejection. This is always positive for all cases. So, sum total may be positive, negative or 0. So, entropy of a closed system, change in entropy of a closed system must be greater than or equal to 0. This is not a correct statement. Next question, a closed system can experience an increase in entropy only when there is energy transfer by heat to the system during the process. So, a closed system can experience an increase in entropy only when there is energy transfer by heat to the system during the process. That is not correct. Even this heat transfer is not there, or there is heat transfer from the system, a closed system can experience an increase in entropy because of entropy generation, right. So, this statement is not correct. Next question, question number 15, constant pressure lines in HS diagrams have negative slope. HS diagrams are very important, and for steam this particular diagram is also known as Mollier diagram or Mollier chart, which is used commonly in industry. So, why this diagram is important is because for working out various changes in thermodynamic properties for analyzing devices in power plants, you may often require the enthalpy and entropy data. So, if you have enthalpy versus entropy diagram, by looking into the diagram you can immediately read out the data. So, the question is constant pressure lines in the HS diagram have negative slopes. So, let us write this TdS is equal to dH minus VdP. Constant pressure line means dP is 0. So, you can write in the HS diagram the slope of the constant pressure line is the absolute temperature, and the absolute temperature is always positive. So, constant pressure lines in the HS diagram will have positive slope, because this is absolute temperature, this is always positive. The next question, entropy of a system can decrease or increase during heat rejection process. So, during heat rejection process this is negative, entropy generation is always positive, sum total may be positive, negative or 0. So, during heat rejection entropy of a system may decrease, it may increase or it may not change. All these three possibilities are there during a heat rejection process. So, entropy of a system can decrease or increase during heat rejection process, this is possible, even it may remain same. Okay. Now, I will come to a different set of short questions. So, this set of short questions, so because this is a review session, I want you to review these following concepts, and I do not want to give you the answers to these learning concepts because we have already discussed in great details, but just consider this isolated system. So, a system that does not interact with the surrounding, closed system, simple compressible substance, pure substance, phase, thermodynamic equilibrium, law of corresponding states, state postulate, flow work, uniform state. So, please try to revise these learning concepts. So, these concepts are important because I mean based on these concepts you can basically develop a foundation on the basic laws of thermodynamics. These are not exactly the laws of thermodynamics, but these are concepts which act as preludes to the practical application and realization of the various intricacies of the laws of thermodynamics. Next, the next questions we will discuss state the assumptions behind the equations that are given. First equation, del W is equal to PdV. So, what are the assumptions for del W is equal to PdV? The assumptions are very straightforward: simple compressible substance and quasi equilibrium process. These are just the two important assumptions, there is no other assumption that goes behind this. Next, del Q is equal to du plus PdV. So, basically it is a first law where you have neglected, first law for a closed system where you have neglected the changes in kinetic energy and potential energy, that is why du and not de, and in place of delta W you have written PdV, that means you have assumed it is a quasi equilibrium process. So, it is a first law for a closed system with negligible changes in kinetic energy and potential energy and quasi equilibrium process. Del Q equal to du plus del W. So, del Q equal to du plus del W is the first law for any process for a closed system. Then next, TdS is equal to, so this S will be capital S, TdS equal to du plus PdV. So, TdS equal to du plus PdV, this is a TdS relationship that is valid for any process. Now, I want to discuss a little bit on this because there are confusions on this in almost all students, that why the TdS relationship is valid for all process. So, if you write del Q equal to du plus del W for a reversible process, for a simple compressible substance you write PdV, reversible process for simple compressible substance, and you write TdS. So, that means this is, you are considering a reversible process of a simple compressible substance, but then how do you claim that it is true for any process? It is true for any process in the sense that if you use this to calculate the change in entropy between two states 1 and 2, you just construct a reversible, hypothetical reversible process and calculate S2 minus S1 using this formula by integrating this. Once you have evaluated this, that S2 minus S1 will remain valid even if you have any other arbitrary process which is not reversible, because it is a point function and all the parameters here in this formula are point functions, therefore it is valid for any process. So, the integration of this formula has to be carried over a reversible path, but once the integration has been carried out, that result can be applied for any process. That is the spirit of calling that or mentioning that this is valid for any process provided it is a simple compressible substance. Next one, TdS is equal to du plus delta W, again here ds will be d capital S, TdS is equal to du plus delta W. So, what are the assumptions? See, this is first law where you have substituted delta Q is equal to TdS, that means this must be a reversible process. You may argue that if it must be a reversible process, why you have not written delta W as PdV? The reason is that it might not be a simple compressible substance, it could be another case where other forms of work are also there. So, you are actually not committing what is delta W, but as you have committed that delta Q equal to TdS, that means you have committed it is a reversible process. The last one, state the assumptions W is equal to minus integral of VdP. So, this is any reversible steady state steady flow process with single inlet and single outlet with negligible changes in kinetic energy and potential energy. The derivation of this formula we have done in one of the lectures, so you already know, but the assumptions we can summarize that steady state steady flow process with single inlet and single outlet and negligible changes in kinetic energy and potential energy. Okay, next question. There is a TS diagram given here, you can see where there are certain lines which are drawn for an ideal gas, and maybe ideal gas, you as a special case you may consider ideal gas with constant CPCV. So, what do these lines represent? So, BA is what? So, this you can tell very clearly. So, it is an isentropic process, no doubt about it, but expansion or compression. So, let us see, let us use the TdS relationship here. So, TdS is equal to dH minus VdP. So, reversible adiabatic process means ds is equal to 0. So, dH is equal to VdP. dH is for an ideal gas is Cp dt. So, as you go from B to A, if you look into the diagram here, if you go from B to A, the temperature is decreasing, that means dt is negative, that means dP is negative, that means it is an expansion. So, it is an isentropic expansion. Next, AC and dA. So, we are trying to consider whether out of these two I give a choice, one is a constant volume and another is a constant pressure. So, out of these two, which one is a constant volume line and which one is a constant pressure line? So, you have TdS is equal to dH minus VdP. So, for constant pressure, now dH is Cp dt. So, constant pressure means dP is equal to 0. So, del T del S at constant pressure is equal to T by Cp. Similarly, if you use TdS is equal to du plus PdV, and for an ideal gas du is Cv dt, for constant volume dV is 0, that means del T del S at constant volume is T by Cv. So, out of these two, which one is more? Because Cv is less than Cp, so T by Cv, this is greater than T by Cp. So, constant volume line in a TS diagram must be steeper than the constant pressure line. So, if you look into the diagram here, AC must be constant volume and AD must be constant pressure. So, out of these two, one is heat addition, another is heat rejection. So, if you have entropy increase, then that will be necessarily heat addition, but if you have entropy decrease, that also must be heat rejection. So, AC is constant volume heat addition, and dA is constant pressure heat rejection, if you have an option between constant volume and constant pressure. EA, what is EA? EA, the temperature is constant, so it is an isothermal process. From E to A, if you are going, it is heat rejection, so it is an isothermal heat rejection process. Okay. Now we will work out a couple of short questions, and these questions are short problems. These questions are typically very short problems. So the question is, this is question number 2 given in the screenshot, but I am repeating this question. A spring is slowly stretched by a tensile force of 1 kilonewton isothermally at 300 Kelvin. What is the rate of change of entropy of the spring per unit length? So this is a case where you have to use TdS is equal to du instead of PdV. Now it is a spring stretching work, that is minus F dx. Why this is minus? Why this is minus? This is minus because when the PdV work is done, work leaves the system, and when the spring is stretched, so or when there is a displacement of the spring with a force, this is the work done by the force, and when you come to the PdV, that is the work done against the resistance. So it is just a different way of looking into it. So you can write, so du is C dt. Under isothermal condition, this is 0. So del S del x at constant temperature is minus F by T. So the spring force is given as 1 kilonewton and the absolute temperature is 300 Kelvin. So you can calculate this one. So the entropy decreases because this is negative. So on stretching of the spring, the entropy decreases. Why? Because if the spring is coiled, there are large number of possible micro stretches for a given macroscopic state, but if the spring is stretched, then the number of possible micro states for a given macro state, that decreases if it is stretched. So less number of probable micro states for a given macro state. Next question, question number 3. Liquid vapor phase change process of a simple compressible pure substance is plotted in a HS diagram. The phase change takes place at 400 Kelvin with HFG value given. What is the slope of the HS diagram for quality equal to 0 and quality equal to 0.5? So basically again we are talking about an HS diagram for a phase change process. So we will use the TdS equal to dH minus VdP. For a phase change process of a simple compressible pure substance, this is 0. So phase change of a pure substance takes place at constant pressure. So del H del S at constant temperature or at constant pressure rather. Constant pressure here means constant temperature also, that is T. So this does not depend on the dryness fraction or quality, it depends only on the absolute temperature. So because the absolute temperature is same during the phase change process, the slope remains constant during the phase change process. So it is essentially a straight line. Okay. Now the final question. This is the final question of this particular session. Heat is transferred from a heat source at 1000 Kelvin to a simple compressible system with a system boundary temperature of 500 Kelvin. During this process there is a total heat transfer of 1500 kilojoule to the system. Entropy of the system increases by 5 kilojoule per Kelvin and internal energy increases by 100 kilojoule. The system mass is 1 kg. State whether the following is true or false. The work done equal to integral PdV equal to 500 kilojoule and entropy generation due to external irreversibilities is 2 kilojoule per Kelvin. So, let us see whether these statements are correct or not. So, let me try to draw a schematic of this. Heat is transferred from a heat source at 1000 Kelvin to a system with a system boundary temperature of 500 Kelvin. So, this is T system boundary, this is T reservoir. There is a total heat transfer of 1500 kilojoule. During the process, entropy of the system increases by 5 kilojoule per Kelvin and internal energy of the system increases by 100 kilojoule, sorry 1000 kilojoule. So, first law, if you apply, Q12 is equal to U2 minus U1 for the system, this is the system let us say, plus W12, it may be a piston cylinder arrangement. So, the heat transfer is 1500 and work is 1000, sorry, change in internal energy is 1000. So, what is the work? That is 1500 minus 1000. So, that is 500 kilojoule. Now, let us do a second law analysis and check the entropy generation. So, we can write S2 minus S1 is equal to Q12 by T plus entropy generation. S2 minus S1 is given as 5. Question is what T you will substitute here? It depends on, as I told, are you interested to calculate only the internal irreversibility related entropy generation or total entropy generation? If you are interested to calculate the total entropy generation, then this should be the temperature of the reservoir, and if you are interested to calculate only the entropy generation due to internal irreversibility, then this is the temperature of the system boundary. Sgen due to internal irreversibility. So, this is Q12 is what? Q12 is 1500 and the reservoir temperature is 1000, right. So, this is 1500 by 1000. So, 1.5, 5 minus 1.5, that is 3.5. I am not writing the units. For this is 5, this is 1500 and temperature of the system boundary is 500. So, this is 3, 5 minus 3, this is 2. So, what is the heat transfer? What is the entropy generation due to external irreversibilities? This is the total entropy generation. This is the entropy generation due to internal irreversibilities. So, the remaining entropy generation is due to external irreversibility. So, 3.5 minus 2, that is 1.5 kilojoule per Kelvin. So, the part B of the answer given, entropy generation due to external irreversibility is 2 kilojoule per Kelvin, that is wrong. It should be 1.5 kilojoule per Kelvin, and the first question W12 is equal to integral PDV equal to 500. See, this is a very typical critical question. W12 is equal to 500 kilojoule, this is correct, but it is not equal to integral PDV because it is not a quasi equilibrium process. How do you know that it is not a quasi equilibrium process? See, there is entropy generation due to internal irreversibilities. What is a quasi equilibrium process? It is such a slow process that the process must be internally reversible. If it is internally reversible, the entropy generation due to internal irreversibility must be 0. So, had this been 0, that means you could have used the formula PDV for the work, but because it is not 0, you cannot use the PDV formula for the work. So, although the work is equal to 500 kilojoule, but it is not equal to integral PDV. So, the first answer is also not correct. Okay, so we have come to the end of this course. We have to summarize, we have discussed various laws of thermodynamics. To begin with, we have discussed some of the basic considerations like system, control volume, the concept of macroscopic and microscopic approach, then properties, processes, states, then pure substance, phase, concept of thermodynamic equilibrium, simple compressible substance, quasi equilibrium process, all these concepts we have developed. Using these concepts, we try to understand how to specify properties of pure substances, how to fix up states of pure substances using the property data or equations of state, and then using that building block we have learned various laws of thermodynamics. So, the preliminary law that we have understood through the concept of thermal equilibrium is the 0th law of thermodynamics. Then we have studied the first law of thermodynamics, then we have studied the second law of thermodynamics, and eventually the third law of thermodynamics, and we have worked out various problems to illustrate these laws of thermodynamics, and these are very critical because no matter whatever is the branch of science and engineering you are talking about, or even it is biological sciences or chemical sciences or physical sciences or mechanical sciences, whatever, or metallurgical and material sciences, the basic building blocks of thermodynamics remain to be the basic laws of thermodynamics. So, that was the agenda of this course. I believe it was enjoyable for all of you to go through this course. It was a pleasure on my personal behalf to deliver lectures in this course, and I wish all of you a great time ahead. Thank you very much.